So once again, welcome to the webinar presentation of Put Your Products in Cruise Control. We're going to be predicting thermal and fluid performance of some products and taking a look at how we do that here at Hawkridge Systems with the software and service tools that we provide. I'm Damon Tordini. I'm the product manager for SOLIDWORKS Flow Simulation and Plastics, and I'm going to be taking you through an overview of what products we provide here at Hawkridge Systems and the associated services that can work along with that. And more specifically, we're going to take a look at how far each of these products and services could get you, depending on where you're at in your design process or what type of a task you're trying to accomplish. As you probably are aware, we sometimes have more than one product at Hawkridge Systems that can accomplish a similar task. And part of what we really pride ourselves on is having a good understanding of when the functionality of one product ends and the other begins. So we believe that we're a great source for giving you that advice on which tool you'll really need to accomplish what you're looking for, depending on the industry you're in, the requirements you have, and your experience as a user. So we're going to be looking at a few applications of some valve performance and thermal performance criteria of a couple different products. And we'll be looking at how the full suite of solutions that we offer fits into that. So we pride ourselves on being what we call a global leader in engineering design and manufacturing solutions. Not just the software, but the expertise in how to use it. Everything from your typical tech support to specialized mentoring and consulting services. We've got a lot of experience, particularly in the field of simulation. And hopefully you've had a good experience if you worked with us in the past. So among all the solutions that we provide at Hawkridge, of course simulation is a subset of that, and we sell a variety of products and we offer a variety of services for a lot of different types of analysis, depending on whether you want to do something like a basic structural analysis in SOLIDWORKS or maybe an advanced fluids problem. We can point you in the right direction. Of course, that's probably one of the most important things you do in any design process next to the initial design itself. We think we're a good source for any of the analysis tools or services you need because of the fact that we have experience in doing design validation for all types of users, everyone from a beginner who's just learned SOLIDWORKS to an experienced analyst who's used a variety of programs over the years. We have a good understanding of how the full process works, not just one part of the solution. So we can take you from doing your initial design, doing analysis at different stages of that design in different tools, and what the best practices are. And that's kind of what we're going to look at today. If we go through a typical product design process or design cycle, what kind of simulations and what kind of products would make the most sense depending on where you're at, what kind of decision you're trying to make. So as you're probably aware, the CAD tool that we provide at Hawkridge Systems is SOLIDWORKS, and so we of course also provide the built-in analysis tools that are part of SOLIDWORKS, such as SOLIDWORKS Simulation, the stress analysis tools, SOLIDWORKS Flow Simulation, which is our CFD tool, SOLIDWORKS Plastics, and SIMULIA Abaqus, which is more of a dedicated analyst tool that's also from Dassault Systems. So we're going to look at the sort of a trade-off of these different products and when you might go to one or the other. Of course, trying to help you guys figure out which of these products to use and how to use them better is a big part of what we do. And we have a kind of a variety of offerings from just getting your feet wet to a deep dive, and hopefully some of you have seen some of the things that we put out on both our website and other sources. We post YouTube and blog videos, YouTube videos, blogs, content on our website all the time, white papers. So hopefully that's something that you've taken advantage of in the past. It's available to everybody. We have our traditional tech support and also our training classes that we offer in our offices and also online via GoToTraining. And we also have mentoring and consulting services. If you're looking for something more dedicated, more specific, where you don't want traditional training examples, but you'd like us to assist you do a real project, we have a variety of ways we can help you do that, whether it's helping you use software that you already own better in a one-on-one situation, or simply completing some analysis for you if you don't own the product yet. And so when we approach these kinds of analyses as part of the services that we provide, there's two main things that we can offer. We can do analysis consulting or mentoring services, depending on whether or not you own the software. But in any of these cases, we try to take the similar approach to any analysis, which is we, of course, have some upfront discussions with you and figure out what kind of information you want to get out of the simulation. And more importantly, we want to understand what decision you're trying to make. What design decision are you trying to make? Are you looking to change a material and get some information that will help you make that decision? Are you looking to make small changes to a design or come out with a new version of a previous product? And gathering that information is key because it helps us figure out how much time you want to invest into doing the simulation and what kind of accuracy you're going to need, what kind of results you're going to need out of it. And of course that helps us decide what product we think you should use, what type of simulation we think you should do. So because of that kind of expertise that we have in doing consulting, we think we're pretty uniquely situated to show you some comparisons of that. So we're going to go through a case study here and look at some different approaches you could take depending on where you were at in the design process of this product. And in the case of this butterfly valve, of course, primarily you probably would have a certain requirement for the design that if you, let's say, were pumping a liquid through this like water, you wanted to know what the flow rate was going to be depending on what position the valve was in. Or maybe you want to know, if the valve was not controlled by an actuator. Maybe if you're wondering, if it was like a free spinning valve, where would that go in the flow? Where would it settle? And of course, overall, you're probably concerned about making sure the valve itself doesn't fail. You want it to provide a certain level of performance without breaking. So again, depending on what stage of the design process you're at, we could do everything from a very basic simulation to an advanced multi-physics simulation to answer these questions. So let's take a look at some different types of simulation, try to contrast them, and see what we would get out of them. So first of all, let's say that we were just at a very basic level trying to figure out more or less where that valve would be if we had a certain amount of water going through the component. If you're familiar at all with the simulation capabilities in either SOLIDWORKS Simulation Standard or SOLIDWORKS Premium, which are those both include what we call static stress analysis as well as motion simulation. Motion simulation is a starting tool, or a good place to start rather, that can tell you what the sort of rigid body motion of an assembly looks like. If you put some loads on it or gravity or springs, it can predict not how something deforms, but instead how the parts would either move around freely in space or would move mechanically based on the mates that you put in. And it's useful for devising things like reaction forces or motor requirements or speeds or accelerations. So it's not typically used to predict product failure, but it can in some cases predict how a product will move. So let's take a look at how that might work. I'm going to open up SOLIDWORKS here. And I'm going to open up the assembly for that butterfly valve. So as you can see at the moment, I've just kind of modeled this valve in an arbitrary position, more or less where I think it might be located. So if I'm really not sure, of course, motion simulation is not going to be able to do any kind of fluid calculations for me. But at a minimum, I might be able to include gravity and maybe a force or some other kind of load that I come up with, which I think will mimic the real-world loads. And so motion can kind of get me a first pass at that, and maybe answer a very basic question about what kind of friction I might want in the interface between the valve and the housing. How easy should it be to spin that? So if I want to answer that kind of a question, I could turn on SOLIDWORKS Motion. It's simply a button on the add-ins pane up above in the command manager. And you may be aware that anytime you have a part or assembly file in SOLIDWORKS, there's a motion study tab down at the bottom here where We can plug in different kinds of loads, whether or not we want certain mates to be active at different times. And then of course the rigid body motion based on that setup will be calculated for us. So what we've got here is the motion analysis mode enabled, which is going to take all of those physics into account and also calculate the right type of results, such as reaction forces. And so I've got a couple loads here. We've got a gravity load that we've applied. That just requires you to pick a direction, of course, and it's going to be normal Earth gravity, 1g by default. I've also got a force that I've applied, and you can see in this case, of course, I don't know what the real forces from the water flowing past this valve will be yet, so I'm going to have to make a big assumption here. And maybe I haven't fully determined what the flow conditions are going to be like in this valve. So in this case, the assumption is more reasonable. So I can, of course, put some value in, some arbitrary value. And again, you need to select some sort of a face or a plane to pick the direction of that load. So I'm just putting a pound down the axis of the tube in this case. And then, of course, there's going to be some damping to how quickly this valve is going to spin around based on the friction in the joint. So we can put things like either just a normal contact between the components, which would have a certain amount of friction, or we can put on something like a damper, where we plug in how quickly we think the energy would dissipate. So if I run this calculation and then play the animation back, we can see here that just based on gravity and based on that load, the valve is going to settle at a particular position. In this case, if we look at it from the side, it kind of looks like the valve is facing backwards and angled a little bit. And that's probably right about where the imbalance from gravity is kind of counteracting the force of the liquid. But of course, the question in the real world is, what would the real liquid forces be on that valve if it was in this position? As you might imagine, the pressures on the valve probably change depending on what position this valve is in. And more importantly, if we're designing this valve, we probably want to know the performance parameters of the valve, like what's the flow rate. And SOLIDWORKS Motion can't tell us any of those properties. So while it might be useful as a first pass, we really are going to need another tool at a higher level to give us the rest of that information. So let's go to the next step here. So to evaluate the valve performance, there's probably two main things I want to know. What's the actual flow rate of the water flowing past the valve, depending on what position it's in? And how is the valve and the tube going to deform under the pressures from that water? Is it possible that the valve would break in a particular situation? Well, we can answer both of those questions using SOLIDWORKS Flow Simulation, which is the built-in CFD tool, and again SOLIDWORKS Simulation Standard, which in addition to the motion analysis capability has what we call static study as part of the FEA tools. So static analysis allows you to put the same types of loads like forces or pressures or gravity onto your model, but instead of showing you sort of a dynamic motion, instead it will predict how something will deform. What is the stress and displacement under a particular load? And of course that predicts material failure like yielding. So we can use both of those capabilities kind of in concert. First of all, let's go back and try to evaluate the valve performance and look at what the pressures inside this unit might be at if we are, for example, simulating water. So I can turn off motion and go enable SOLIDWORKS Flow Simulation instead from the same add-ins menu. So here again, I've just got my valve in sort of an initial arbitrary position, and maybe one version of this valve is going to be mechanically controlled. And so if that's, for example, the starting position that it's in, and I want to simulate that with SOLIDWORKS Flow Simulation, all I really need to do in this case, since it's going to be an internal fluid analysis, is to close up the openings in the model. And that way Flow Simulation will detect the fluid region, which will allow me to put in my boundary conditions like a flow rate, and of course it'll do all the calculations. Here I'm going to use something called the Create Lids tool to prep this model for flow simulation. So I can click Create Lids, and I'm just going to select the flat faces on the front and back of this valve, and you can see right there Flow Simulation is giving me a lid with automatic thickness, and that will detect the fluid region for me and also give me a location that I can click on to apply my flow conditions. So let's switch over to this other configuration here where we've got those loads in. And that's a common practice, by the way, because you may also want to make other changes to your model, like suppressing parts you don't care about or modifying the geometry in some way just for CFD. And once we've done that, we can detect the fluid region automatically here. Looks like we're good to go. There's the fluid in the blue region. And then, of course, we could start a new analysis, which we normally do with what we call the wizard. So the wizard walks you through the required stages of setting up a new project in Flow Simulation. Everything from giving it a name, let's say, inlet static pressure 30 psi, something like that. Picking your unit system, of course, American units in this case, if we want psi. Specifying what kind of physics we want to include in our simulation. This is an internal analysis in this case, and we might decide to include both heat transfer effects, even radiation if that was a factor in a very hot environment or something outside. Gravity would be available, and even the ability to do a time-dependent analysis to see, for example, how changing flow rate over time or changing pressure over time might affect the performance of the system. Of course, we have a library of fluids we can select. In this case, we're going to go with water. And we can plug in our wall conditions and our initial and ambient conditions if, for example, this is in a hot or low pressure environment. So when the wizard is complete, we really only have a little bit more work to do, and that would be to put in what we call the boundary conditions, the flow rate or the pressures that we want to assume at the inlets. So for example, in this case, maybe I've got a pump that is providing a certain amount of pressure to the inlet of this valve, and depending on the position of the valve, that's probably going to result in a particular flow rate. So I could select the inlet. I could either define that flow rate as the fixed value, which of course would change the pressure, or if I've sort of already selected the pump I wanted to use, I would input the pressure and see what flow rate it gets. So kind of whatever variables you don't know the answer to yet, you can plug in the information you do know into Flow Simulation, and the rest will be calculated for you. So there's a certain inlet pressure, and then of course I could do just a normal ambient pressure at the outlet, and that's going to give me some flow from inlet to outlet, from high pressure to low. There's also different kinds of measurements that I might want to take. The flow rate, of course, the velocity, maybe the pressure drop from inlet to outlet. And in terms of this valve itself and where the valve would be, I might also want to look at what the torque on that valve is. Of course, if it's mechanically held in place, I would want to know that torque to make sure that my motor can provide that amount of force to hold it against the flow. Or if it was a free spinning valve, that amount of torque that the flow is putting on the valve would be really important for me to know, because that's going to determine if the valve would really be in that position or not. So for example, here's kind of a first analysis that we've done, just assuming the valve would be here. And when we run the simulation, there's different kinds of results we can get, of course. Everything from a cut plot showing the velocity and showing the streamlines, whether or not there's recirculation. You can see here that, of course, the water is being forced around the narrow opening of the surrounding the valve, and that's causing the velocity to go up. And we've got some downstream recirculation, of course, and we've got a pressure gradient on the valve itself. And that pressure gradient, of course, is what's causing a little bit of a torque there, right? It's going to be pushing the valve, in this case, sort of in a clockwise way, whereas the weight of the valve itself probably was causing it to sag down and would counteract that torque. So what if we wanted to know where the valve would actually settle on its own naturally? Well, one of the benefits of flow simulation is that we can do something called a parametric study to rerun the simulation in different positions, whether that means changing the dimension on a model and changing the size of various features, or just changing mates, or maybe changing flow conditions or material properties. So we can create this new parametric study which I've got here, and we plug in what variable we want to change in the parametric study. In this case, I've got a mate that's controlling the angle of that valve. The mate is up here in my favorites folder. Right now it's at 30 degrees. And I'm not really sure, again, where it would really be in actuality if it wasn't fixed in place. So I can go in and type all the values that I want to try for that valve position. In this case, I'm going everywhere from 30 degrees up to 60 degrees. As I can see right now that there's a lot of pressure on the top of that valve as it is. So when I set this up, I can also pick the kind of output I want from flow simulation. So here I'm specifying that I want the velocity, and the torque, and the pressure drop for all of these different positions. And I would go to the Scenario tab, and this would allow me to hit the Run button, which would simply recalculate my analysis, change the value of that mate, and then run it again. And what I'm presented with is basically a batch run. I've got, in this case, 7 different analyses with the valve in the different position that I can look at. So here I can, of course, see that as the valve becomes sort of a more shallow position, the pressure drop is more or less staying the same, but the velocity is changing quite a bit, and of course the flow rate would change accordingly. Basically, as the valve opens up more, the velocity, the average velocity goes up, which is about what you'd expect. And you could see that visually by looking at, for example, the cut plot that we had created. So this right away would help me make sure that the valve is going to perform accurately and deliver the right flow rate no matter what position it's in. Of course, I probably have some sort of curve that I want to meet. That's part of my product requirements. But the secondary part of that question is, where would the valve actually be? You know, what position would it have settled in if it wasn't fixed in place? Well, if I know what the mass of this valve is, I can probably guess at what sort of the torque on the valve is under its own weight. I may have been able to find that from the motion study we did earlier. In this case, I looked it up, and it's about 1 pound-inch. So about a pound-inch of torque is from the weight. We'd be trying to pull this sort of in a counterclockwise way back towards the vertical position. So at what position here is the torque from the flow going to match that? Well, all I need to do is go look at those results again, and I have the ability to actually see this represented as a chart. Here's the trends for velocity, and torque, and the pressure drop. And I can see right about here is where it would be, the torque from the flow would be equivalent to the weight of the valve. And that is right between design points 4 and 5, which in this case were 45 and 50 degrees. So something like maybe 47 or 48 degrees is probably where that valve would end up. I could confirm that by creating a new project from that design point and then simply going and running that simulation again on its own, which I've done here. You can see that now I've got this new configuration and a new flow simulation project with that position here. And if I simply click the Run button, I could redo the analysis or load in my existing results. This one takes about 44 seconds to run, so we can go ahead and do that computation right now. This is going to generate the mesh and then solve the job locally on my machine, of course. And those goals that I was looking at, things like the flow rate, the velocity, the pressure drop, not only are they valuable for giving me quick feedback on the performance of the product, but it actually helps the simulation check the accuracy of its own result. So this is going to run for a few iterations here until it finds these goal values sort of leveling off, and that means it's found sort of the steady state operation where everything's in equilibrium. So I would expect that that torque value is going to be somewhere near -1 pound-inches, because that's what I estimated from my parametric study. So it's a little bit of a sequential process here. It's definitely not an automatic solution to find all aspects of how this would behave, but flow simulation makes it pretty easy to try comparisons like this, thanks to the quick setup and thanks to the parametric study capability. And if I wanted to know now what maybe the stress or displacement on the valve is going to be in this position, I can export all of these flow results that I've just calculated to a stress analysis with SOLIDWORKS Simulation Standard. Again, we're talking about the surface contours of pressure here, and of course all the velocities and things. Those pressure profiles on all the components are a load, and rather than guessing at the load for a stress analysis, they can simply be sent directly. Again, as sort of a sequential operation. All it requires here is you go to the Flow Simulation menu, Tools, Flow Simulation, Tools, and there's something called Export Results to Simulation. If we click that button, we're able to go over to the SOLIDWORKS Simulation add-in that's built in, and I can create a new static analysis. And again, a static analysis tells me what the stress and displacement of my model are under static loads, non-changing loads. And so I've got a static analysis here where instead of putting in just a force like I did in the motion study earlier, now I'm able to import the flow effects from that CFD analysis that I just ran. So of course the pressure gradient you saw on the valve itself is going to be mapped directly in here. And I can also put in, of course, the fixtures that I want and other loads like gravity. And you can see here that the material properties have already been applied, in this case alloy steel, and that's going to affect the loads due to the weight of the parts of gravity, and of course how stiff the material is. So we can create this mesh as well, which is going to look a little bit different because this is a finite element mesh for our structural analysis tools. There you can see it's automatically generated using, in this case, solid elements, solid tetrahedral elements. And if I hit run, I'll get some results, in this case stress and displacement. I can animate these, of course. I can see that looks like the stress primarily would be concentrated in the hinge of the valve itself, sort of the pin that fits into the shaft. And I can see how much the valve itself displaces under those loads as well. It looks like it might deform very slightly at the edges, and maybe there's a little bit of sag in the tube. Of course, all of that would depend on the flow conditions and how much pressure was in my first analysis. So with this kind of a process, it's usually very practical to evaluate a product in a lot of different scenarios, try different design changes to the product, and then once you have decided the flow conditions that you want to assume, those loads can be sent to a stress analysis as well. And that's commonly used for things like wind loading or thermal expansion problems. But what if the flow and the structural behavior of something are kind of dynamically linked and they interact? We know in this case, for example, we had to use sort of a roundabout method to figure out where this valve would actually end up if it wasn't fixed. Well, in those situations, depending on the level of realism you need, sometimes the SOLIDWORKS simulation or SOLIDWORKS Flow Simulation tools might not be able to give you all the capability you want. And if you're really looking for a high level, very advanced analysis, rather than something that a typical design engineer or mechanical engineer would do, that's the reason why at Hawk Ridge we offer another package called SIMULIA Abaqus. Of course, this expands the capability of just the SOLIDWORKS simulation tools into the realm of the dedicated analyst who has access to a lot of different types, not only of meshing techniques and material models, but actual calculation and solver capabilities, including smooth particle hydrodynamics, coupled Euler-Lagrangian, which are ways of dealing with fluids, to adhesive models, crack propagation models, and a host of other things that can really explore how the interaction between different physics affects a product. So for example, in this valve, we want to know, would the valve not only change its position depending on the flow conditions, but also what if it moves around over time? What if the flow oscillates around the valve, both top and bottom, and causes it to vibrate back and forth? That might be that valve flutter might be a problem as far as delivering a consistent or smooth flow to the end use. And there's other applications similar to that, like wingtip flutter. So when we know that the fluid and structural behavior is sort of interacting and codependent, we need a multi-physics tool like SIMULIA Abaqus to do that. Luckily, as I mentioned, we have pretty good experience with how to use SIMULIA Abaqus in conjunction with SOLIDWORKS, and so we can point you in the right direction of a good workflow, for example, using the SIMULIA SOLIDWORKS associativity. The associative interface is an add-in for SOLIDWORKS, which allows you to take your model and with one button you can export it directly into the Abaqus CAE interface without having to manually save out a file type or convert using some other format or importing errors or resolving importing errors. So by using that associative interface, your SOLIDWORKS model will appear instantaneously in Abaqus CAE, and of course if you change the model in SOLIDWORKS you can update it with the same process. And so in Abaqus CAE there are a variety of other options, of course, for the setup. Since it is a dedicated analyst tool, everything from different types of mesh elements, hex elements, in addition to tetrahedrons and other types of brick elements. And once we were to run that kind of a simulation, because we can enable both the structural and, for example, particle capabilities in the Abaqus solver, we could get this true, what we call FSI, or fluid structure interaction. So things like the free spinning valve position automatically being determined based on the flow conditions, the stress or deformation in the valve being simultaneously calculated, and the prediction of these dynamic effects that might be occurring on the valve, whether the valve flutters, how that changes the flow rate of the valve, and even how that valve may move and alter the flow under changing input conditions too. For example, if the pump that's supplying the water here starts up or shuts off or cycles. So again, certainly this is a more direct way to answer a lot of the questions we were looking at earlier, where it might be a more complex simulation, but it also is much more realistic in pretty much all senses of the word. Another similar case study to that would be something like a power supply or other electronics product, usually in some type of an enclosure. In this case, we've got cool air being sucked into the enclosure through vents, and of course an exhaust fan that's pulling the hot air out after it's warmed up by all the components inside. We probably would want to evaluate the heatsink and heat spreader design on some of these components, the packaging design, whether there are vents or where the fans go. And of course I probably want to ensure that my parts don't get too hot while minimizing the cost of manufacture and production. So here's another scenario where, depending on what stage of the design process you're in, a different tool might be the best fit for you. For example, if you're at a very early stage and you're trying to do something fairly simple like evaluate a heat spreader, picking the material of a heat spreader or maybe what thickness the heat spreader should be to get the heat out of a chip, in that kind of a situation, the thermal study in SOLIDWORKS Simulation Professional, which does not do any flow calculations, is probably a good fit. If you've got a fan or something blowing on that heatsink, the airflow conditions probably won't change very much. And so the thermal FEA study can provide a lot of value there without sacrificing accuracy. Of course, if you want to start getting into design decisions that do heavily depend on the airflow, like where the vents should go or where the fans should go, you're going to need to move to a CFD tool, in this case SOLIDWORKS Flow Simulation. And Flow Simulation is a great fit for that application because it does the heat transfer integrated into the calculation. So in some sense, it does do multi-physics for certain types of problems, thermal and flow at the same time. There's also an available add-on module for SOLIDWORKS Flow Simulation. Some of you may be aware of it, called the Electronics Cooling module. That has a variety of features that enhance the realism and accuracy of things like the components on your PCB or the properties of the circuit board itself, or even handling things like heat pipes or electric current in a wire or a trace on your PCB. And then finally, again, if there is some sort of a structural component to the way the product behaves that is important to look at simultaneously with the flow or thermal behavior, that's where you'd go into the realm of SIMULIA Abaqus for a realistic multi-physics simulation. In this case, typically the desire in that type of an application is to predict things like thermal stress, particularly if you're worried about components separating from the board, maybe solder joints breaking. And of course, if things like that happen where there's separation between components, that would affect the heat transfer properties. And so flow simulation would have some limitations in that sense, because SOLIDWORKS Flow Simulation just doesn't have the ability to handle that kind of a deformation. So again, depending on sort of what stage of decision making you're at, if you're kind of on a finalized design like this and you really want to predict the behavior of a real-world physical test as accurately as possible before you build that prototype, in many cases SIMULIA Abaqus is the best fit. Of course, these types of tools, fluid and thermal analysis, are widely used in all industries that we have customers in, everything from aerodynamics analysis, industrial equipment and machinery like heat exchangers or intakes, valves, consumer products, vehicles, including cars, aircraft, and equipment that goes on those vehicles, and even biomedical. You can see there's a stent with blood flow in the bottom right-hand corner. So whatever your application, we've got a good amount of experience among all the customers that we have at Hawkridge Systems. We can probably point you in the right direction of which tool is going to be their best fit depending on the decisions that you're trying to get out of it. And we have a good amount of experience on the simulation team here at Hawkridge. We've got over 40 years of combined experience doing FEA, CFD, and other types of simulation. And we've got over 1,000 customers that use these tools, again, in a variety of industries. So we've seen a pretty large amount of the spectrum, and we can tell you what we've learned from that interaction. We also, of course, do consulting projects, as I mentioned. We do over 30 of them every year, and using a lot of that knowledge is what is why we produce webinars and tutorials, blogs, and all the other content that we try to put out there to help educate everybody. And just to give you an example, some of the services jobs that we've done in this realm with are things like simple SOLIDWORKS simulation static analysis. We did a situation where there was a basic thermal stress problem, and the customer was concerned about fatigue of that stress. So that involved doing a thermal analysis to estimate the temperatures in basically a conducting piece of copper, figuring out not only how hot it got, but how much stress there would be from that thermal expansion, and then doing fatigue analysis to predict the life. We did something similar to that for a brake manufacturer who was trying to evaluate the design of their rotors to improve cooling. And we've also done some weld failure estimation in SIMULIA Abaqus, also related to fatigue life, when fluid structure interaction was the key. So to sum up, we feel that we've got the answers that you guys need, and that we have the tools that offer the different capabilities that you guys need. So we welcome you to challenge us. If we can't get you an answer, we will find someone who can. So please feel free to reach out at any time if you think that we might be able to help you in any way. And of course, hopefully you're getting some value out of the webinars that we've been doing this month as part of Simulation Month. Today was fluid and thermal analysis, and you may have missed last week was the dynamic and fatigue analysis version of this, where we covered basic stress analysis, fatigue, shock and vibration loading. There's a recording of that webinar that will be put on our website soon, and we welcome you to attend the last of these 3 webinars. It's going to be next Friday, May 26th. Myself and Tim Milo, who is the product manager for SIMULIA Abaqus, will be covering how you can do manufacturing simulation with the tools that we provide. Everything from plastic injection molding, extruding, metal forming, and so simulations related to creating a product for the first time rather than estimating how it behaves in the real world. So please sign up for that. You can do so on our website and under the events section. And also feel free to go look at the Simulation Buyer's Guide, which is sort of a written form of all of this content, also available for download. With that, I thank you for your time, and I hope you have a pleasant weekend. Thanks again.